Hello everyone, and today we're going to be talking about backpropagation, which I would say is one of the rather harder topics in machine learning. So because it is very like math heavy, so don't worry if you kind of don't feel like you don't get it at first. It's completely fine. So first things first, I would say that the prerequisite for this is at least watching the perceptron video, where we calculated how a perceptron works, because backpropagation is basically something really fundamental, which is part of a neural network. So let's say I have a neural network here with two inputs, with two nodes in the input layer. Let's also have two nodes hidden layer and one node in the output layer. Output layer. So the input layer is all of this, the hidden layer is all of these nodes, and the output layer is all of this. All these nodes here, they are connected to each other, and then this one is connected to this one, and this one is connected to this one, right? Given this neural network structure right over here, this is a neural network. We have some kind of data, we have some kind of inputs, such as 5, 4, for example. Let's say the network gets 5, 4 into it, and then it can predict, it will make a prediction based on this data that it's coming in, and it will make a prediction of what it thinks the data will be coming out. So let's say we get 5, 4, and it goes through all of these weights, and it will return 255, for example. And 255 might seem like a very random number, right? But let's say that the two inputs that we have right now, they actually do mean something. So let's say that this is power, where we have like a data set of a forecasting system, right? One is going to be power, another one is going to be like wind speed. So imagine this is like for a wind turbine. Oh my god, yeah. And then the wind is like blowing through it, and it gets power by the wind blowing through it. And let's say that the prediction, it's going to predict, okay, given the power currently and the wind speed currently, what do you think its next power is going to be? And so it's basically trying to predict that, like, okay, if we had 5 power now, 5 power, and we had like 4 wind speed, what, like in day 5 or something, right? Like in day 6, how much power are we gonna have then, given the two datas that we had previously? This is very, very simple, right? And let's say what it outputs is 255 power. That like, oh, okay, like the neural network says we're gonna have 255 power, right? And the prediction is wrong, and the reality was that it was 6 power on day 6. And because the neural network did a wrong prediction, we have to update all of the layers. We have to update all of the weights. I explained this very like as a black box right now, where I said that, okay, we're gonna have these inputs, this is gonna be the output, but how are we gonna calculate this, right? So how is this neural network calculating all of this and comes to these numbers? And so now that we kind of have like the intuition about how it's supposed to work, we can start to actually delve into the math about how it actually works. So a neural network, everything starts with something called feed forward. And feed forward is exactly what we were talking about, which was this like prediction of 5, 4, and 255. Let's just say that. So what the network did right now is it took this input data, it passed it through all of these nodes, and then it outputted it and then it outputted its prediction, right, or what it thinks the value will be given these two inputs. What this whole operation is called is basically, it's called feed forward. And we're gonna change the numbers a bit so that it's gonna be a bit easier for me to explain it. The thing is that we need to first name all of this. So let's name this for I1 because it's the first inside the first input, and I2. And so if you've watched my perceptron video, you might think that like, oh, okay, the node has like 2-3 input layers, right? And then it's supposed to like output something, right? Here it's the first nodes in this input layer is actually works very differently. The input nodes are actually these things. So they're like, if you watch the video on the perceptron, you should most likely, I'm just gonna say it right here. This thing, the input of the perceptron, there categorizes these nodes, right? These nodes do not have something after them. That's not they are inputs in of themselves, and they're just kind of visualized as themselves as well. The weights that we talked about in the perceptron video, they're actually these things right over here. So you would think that if you think when we looked at the perceptron, it's actually the hidden layer that is kind of like the most similar to a perceptron. It's actually the hidden layer that is actually acting as a perceptron right now, meaning that given this architecture, right, with like your activation function, sum it all up, weights, weight 1, weight 2, weight 3, and then you know, like the output. The reality here is that what's acting as a perceptron in our case is actually these things, right? So these things actually have an activation function for each of their individual nodes, and right now we only have 2 input layers, so we don't need this, for example, or like we don't have an extra weight, so they only have 2 weights, which is gonna be the input I1 and I2, right? And the output, which is, we can just call it out or something, right? This is basically kind of like, in a nutshell, how this perceptron here operates. Just so it's not kind of confusing, because it might seem a little bit confusing that like, oh, well, the input layer, you said like, people say that like, oh, the input layer is a perceptron and the output layer is a perceptron, or they look like perceptrons, but they have kind of like, they don't, like I said, they are just these things right over here. And now we can start naming all of this, right? So let's say that this one is H1, or this perceptron, it will be called H1, this perceptron will be called H2, and we're gonna call it this one the output. And each weight is gonna be initialized with its own values. So let's say this one is 0.11, this one is 0.21, this one is 0. Oh, actually, to make it a little bit simpler, we can do 0.12 and 0.08. And we have 0.14 and 0.15. Okay. So you might be wondering like, oh, okay, where do these numbers come from? Why do we have like a bunch of zeros and everything like that? These are just randomly initialized once you make the neural network. So once you build all of this, you just kind of, literally what people, what some scientists do is that you would just randomly choose starting weights. So you would randomly choose numbers to start with. Because it doesn't, the most important aspect is not like if you have chosen the correct weights, because we're going to be updating the weights. The whole point of this backpropagation algorithm is to update all of these numbers. The input goes through these numbers and they affect the output. So all of these numbers are actually affecting the output. And backpropagation, what we're trying to see is that how much did this little weight right over here affect our prediction, which was 255, right? And now to remove this 255, we're gonna make it a little bit more simpler here. So let's say we have our inputs. So our inputs inside here is 2 and 3. And remember, what's inside the node and what's the weight of the node are two different things, right? And so when we're doing backpropagation, not only do we need to change inside the node, we also need to see how much of an error this hidden layer gave us, and not only the output layer. So we kind of go backwards, right? So we need to calculate this weight, then we need to we need to update this weight, then we need to update this weight, then we need to go into here. We need to see, okay, how much of an error did this have? And then we need to go up and update this weight and go and update this weight. And the same goes for here. We go into here, we calculate how much of an error this had. We update this weight and we update this weight. So you can say backpropagation, and this is kind of like in the word where we're like backpropagating all of this. But just remember that like we're going from, like, imagine like you're reading manga, right? You're going from right to left. So you're going from the output layer, you update this, and then you check how much of an error this gave you, and then you update this. So you update all these connections. You can see there's a connection here. So you update the weights that are connected to it, and then you move on, you update the weights that are connected to here. You don't need to update the input because the input is the data set, right? We don't want to change the data set. We just want to change the calculation of it. So for people who are wondering, you only need to update all of these weights. And that's the most important thing in backpropagation. Feed-forward is also a term that can also describe a neural network architecture. So feed-forward neural network, and then usually we're calling it neural network, is basically a neural network that can only do this, that we talked about. That doesn't have backpropagation. It can only go from the data that we talked about into the output, and it has no learning. That's basically what feed-forward neural network means. There's also another one, another way of naming it. So we're gonna have like a little bit naming definitions. Forward pass. So the forward pass is basically like an action, like something you're doing, right? We're forward passing this into here. So it's basically the same thing. It's just it might be a bit hard with the terminology, but forward pass just means basically the act of doing this. Meanwhile, feed forward neural network is basically describing a whole architecture that does this. And just for clarification, right? Because I wrote feed forward, but what we're doing right now is forward passing, but it's completely the same. It's the same concept. So first, what do we need to do in a forward pass? We need to take our input. I realized I made a small little typo. I swapped these two to have the correct color. Basically, again, what's gonna say is that like we're looking at, or what we want to do, we want to calculate H1, right? And we want to calculate H2 as well. So H1 has the blue weights right over here. To calculate H1, we will need to take this weight and this weight because they're the ones that are connected to this. And we also need the inputs, right? And on the other side, to calculate H2, we would need this and this. And also these two inputs. There we go. How do we calculate this, right? So an important thing to see before we start is that H1 is affected by both the the first input and the second input because of these lines, right? So we need both of them to be affected. So let's just say that we have 2 and we have 3. We're going to be having to multiply each of these with 0.11 and 0.21. Oops, 21. To simply explain this notation is basically we have a matrix set. So how this is going to work is that we basically have a matrix multiplication right now. But the most important thing that you need to take away here is like 2 is going to be multiplied by 0.11 and 3 is going to be multiplied by 0.21. So what is actually happening here is that we do 2.0.11 and what it equals, and then we do 3 times 0.21, which is going to be equals, right? 2 times 0.11 is 0.22. 3 times 21 is 0.63. Now we take both of these results and we add them together. So 0.22 plus 0.63, we're gonna get 0.85. And 0.85 is actually gonna be our H1. So we just calculated the sum for H1, which is going to be 0.85. Boom. And now what you might be guessing, we need to do the same thing for H2, right? With these kind of things. So we need to take the input of this layer, we need to take the input of this layer, and now we need to multiply it with this weight, and we will get the output, right? And the beautiful thing about matrix multiplication, which we will talk about right now, is that like you can put in more of this. You might be thinking like, oh, why do I have to learn matrix multiplication in neural networks? Why is that so important? Well, it's actually really important because it's efficient, right? So we just calculated one thing, right? So instead of calculating it one weight at a time, you can actually calculate it multiple weights at a time. So what we just need to do is have this 2, 3, and then you multiply it, and you can say that we're going to be multiplying it by 0.11, which is this thing, and 0.21, which is everything we just did. And you can also add in the matrix multiplication 0.12 and 0.08. So in this matrix multiplication, you can see that we just added the input layers into here, and we added both the calculations for this neuron, and we also added the calculations for this neuron right over here. So we added the weights for this neuron as well. So this makes it so that we can very effectively calculate this, because the way the matrix multiplication works is that this thing right over here will always be multiplied with these values, and this thing right over here will always be multiplied with these values, right? And that is super efficient because we basically, we're kind of think of this as like grouping them together. We can kind of like very quickly calculate both H1 and H2 using this matrix multiplication method, right? And so how this will work, we're gonna have 2 multiplied by 0.11. I'm gonna say 0.11. Actually, to not confuse you, let's just do 0.11 plus 3 multiplied by 0.21. So you can see that 2 multiplied by this, 3 multiplied by this, 2 again multiplied by 0.12 plus 3 multiplied by 0.08. You can see we get 0.85 here, and here we get 0.48. We don't really need, because like right now you can see, well, like what we did, all of this, we got one value. What of this, we got the second value, we did all of this. Well, what we can actually do is we can group them as well. We can group them into a matrix, and the result of this matrix multiplication will actually be 0.85, 0.48. So this is basically the beauty of matrix multiplication, is that all of these calculations that we did, and we're like, oh, okay, well, where do we put this? Where do we put that? We can very cleanly visually show it using matrix multiplication. So now we can very clearly see that, okay, this is going to be H1 and this is going to be H2. And guess what? If we add more layers, if we add more neurons, more inputs, all of this, we can still just put it in a matrix. So we can just continue expanding this matrix in this direction, actually. And then we can continue expanding the weights in the other direction, right? And the outputs will be like, oh yeah, let's say we have an H3, H4, right? So you can kind of see that the math here is actually just made to sort of simplify all of this. Like we're just, what we're trying to do with matrix multiplication essentially is just simplifying all of these operations. So we don't need to type out all of these kind of things that we just did, all of this, like all over right over here. Nope, we don't need that. We can just very visually explain it. And I'm really trying to drill kind of the beauty of matrix multiplication here, because for the first time, for me at least, it was kind of like very confusing. Well, what's the point of using matrix multiplication? Why are we doing this? Like, yada yada yada, you know. And now I kind of understand that it's just like a very simple overview over how all of this works is through matrix multiplications. And so what we basically did, we found the value for H1, H2, which is 0.85, and let's do 0.48 here. Well, we have to keep going, right? Now we have to calculate the output, right? And how do we calculate the output? Well, we just need to take these values, right? So we take 0.85, 0.48, 0.48, and then what do? We matrix multiply them. So we multiply them by these two weights, which is going to be in this direction. And be really important when you're doing matrix multiplication that you will get very different results if you put it on top of each other or next to each other. Like, the direction actually plays a role. Just remember it, because like here you can see 2 will be multiplied by these two, and 3 will be multiplied by the ones under it. And it's kind of the same with all types of matrices. So just to remember that, right? Because you can mess up the calculations a little bit. To kind of showcase what's happening, we have 0.85 times 0.14 plus 0.48, which is this thing, times this thing, times 0.15, right? And this one in the end, just gonna look at my notes here, we have 191. There we go. So we basically did everything we just did here. Got the results on them together, all of this. I just kind of like, we just skimmed through it a little bit, doing it a little bit faster, because once you understand the fundamental of how this works, you can kind of see that it's just like repetition. Like now we looked into matrix multiplication, we know how to do matrix multiplication. We can see now that all of this it's just essentially matrix multiplication. So you can see like our results here is going to be 0.191, and our answers 0.191 is gonna be actually our output. So remember guys, when I was talking about like power and predicting the next power, and it predicted something 255, well, this is our prediction. This is what we basically we got our input 2 and 3, and given these weights that we all went through, we predicted that the number is going to be 0.191, right? And it might seem very like, oh, well, what do these numbers mean? Like, what is going on? It really depends on the problem you want to do. The thing about neural networks is that you can actually apply them into many different things. As long as the problem that you have, you can write it into numbers, then you can essentially make a prediction model from it, right? So let's just say like our input will actually be a pixel, right? Like an RGB, red, green, blue, right? But then it has 3 inputs because it's red, green, and blue. But for simplicity, let's just do red and green. So this is the amount of red that is on the pixel, and this is the amount of green that is on the pixel. And then what you can do is you can use all of these weights to predict whether this pixel is a part of an animal or a part of a building or something like that, right? For example, let's just say that like it has a lot of red, then it's very unlikely that the pixel will be part of an animal, because there's very few animals that have red pixels. This is very simplified, but it's just kind of like to give you an intuition on how we can apply neural networks into different domains. All right, but let's focus on our problem right over here. What we basically did right now, like what this whole operation here just did, we just did a forward pass, right? Let's just say that we predicted that this is going to be 0.91, but we predicted wrong, right? Because the true value, the true value, or actual output, whatever you want to call it, the true value, so what you were actually supposed to predict, is just 1. So you were just supposed to predict 1, not 191, right? And this is where we need to start doing backpropagation. Hope you guys are doing well. Get some C or something, because now we've kind of like, we're halfway there, right? Like we did a forward pass, now we just need to start backpropagating, which is like, okay, we guessed wrong, we need to update the weights. How do we do it? And the way, first we can also calculate the error. We can calculate, okay, how much of a difference is this error compared to the true value, right? So you were supposed to be predicting 1, but you predicted 0.191, right? So what we need to do is calculate what is our actual error here, right? And this is a formula. So this is just very simply, I'm just putting these numbers into a formula. So to calculate basically the distance, are like how big of an error we have, right? Is 0.91 minus 1 and times 2, right? And then we're gonna get 0.327, which is basically we want to minimize this error as much as possible. So if we get a bigger error, that's worse. If we get a lower error, that's more correct, or that's what we want. We want a lower error, not a bigger error. Remember that our prediction right over here, prediction is actually based on the output. So our prediction of this error is based off the output. Remember that we want to reduce this error. We want to have as small error as possible. So 1 on 91. So our prediction compared to the true value was wrong, and we want to calculate how much wrong was it. Well, it was 0.327, right? And now we need to understand that this error, or like our whole kind of like, yeah, this, our prediction, our error, everything here is calculated by all of this forward pass that we just did. So everything that we just did with this matrix multiplication, all of this, it's basically how we got to the prediction that we have right now. And mathematically, it is made like this, right? You could deconstruct it, right? So you can say that our prediction, is because of the H1, H2, is because of H1 multiplied by the weight. We were just gonna name this weight 5 because I did not have a naming for this, but and then plus H2 multiplied by the second weight, so multiplied by this, right? So we can say that like, okay, so the reason for our error is because of these guys, and then we can deconstruct them more, that the reason for these guys' error is because of these guys, right? Like this guy and this guy is the reason that I have this number, right? And the same with this guy is like, oh, okay, I made an error. Okay, so you're telling me I have an error. Okay, I made like 0.327 is the error, right? And we're basically asking, okay, this neuron right over here, how much did you contribute to this error, right? And the neuron is basically like, oh, well, I am not the only one, like, I am not the only reason. My contribution, his contribution was 4.48. He's basically saying that like, oh, well, the reason I have this number is because of these weights, right? So you don't only look at me, look at these weights right over here, right? I wasn't the only one responsible for the error. If we basically make it even more, we have I1, W1 plus I2, W2, and weight 1, weight 2 is basically these two. The reason for H1 was actually because kind of started drawing the formula. I might as well make it whole thing. It's a little bit too, this might be a very long formula, it might be a little bit too confusing, but the most important thing is kind of like what I was just saying is that this guy H2 is saying that like, oh, I am not the only one responsible for this error, for the prediction. It is actually also these two weights, like these two red weights here, they're also responsible, right? And H1 is basically saying the same, that like, I am not the only one responsible for the error. It's also these two blue weights right over here, because they're connected to me. Well, it's, and also the input, but we are not going to change the input, right? Yeah, and also the input, but we will not, the input is not the important thing. What's important is changing the weights, right? We want to minimize this error, right? And to be able to minimize this error, what do we need to do in this whole calculation right over here? Well, we need to change all these weights that affected this error. The weights that affected this error was all of them, because they're all connected into each other. Our notation for all of this that I just said, which is basically explaining, okay, well, how much did this guy contribute, or how much did this weight contribute to the error, and how much did this guy contribute to the error, and how much did this weight contribute to the error, or contribute to the error / prediction, right? How much did this thing contribute to the prediction? How much did this contribute? to the error, we will use something called the chain rule, right? And that is the change. My deltas are really bad. I'm sorry, guys. The change in error given the change in weight 6, which is gonna be, say this is weight 6. Actually, to make it a little bit more understandable, given weight 6, this notation might seem very like, oh my god, what is going on? Why is there like division? Do I need to devise error by? No division, no, not this is derivative, this is deltas, this is change. So when we're writing it, when we're noting it like this, you do not do the error divided by 0.15, right? None of that. This is just a mathematical way of showing that we are trying to understand how much this weight, we're trying to understand how much this thing contributed to the error. That's the most important thing with this notation. Like, we're not trying to, like, we're not doing fractions or whatever the hell. We're just like, what this notation means is we can almost say it like, how much can we change the weight, and if we change the weight, how much will the error change? So let's say, like, we just did all of this, right? But let's say this thing, instead of 15, it was 45, right? And if it was 45, how big of a change would it give to the error? That's essentially, would it go down? Would it go up? Right? Like if we do a less number, if we do 0.05 instead of 0.05 instead of 0.15, we're making it less, right? And so, like, if we change it to a lesser, if we change the weight to a lesser number, will that make the error go up, or will that make the error go down? That's what we're trying to figure out. So this is the point of this notation right over here. We're just trying to see how much does changing the weights mean that we're going to change the error. And by understanding this way of writing it, we can see that, okay, to understand how much the weight changes the error, we also need to understand how much the error changes the prediction. The error changes the prediction multiplied the change in prediction in given delta weight 6. Okay, so we're gonna go through this because there's a lot to unpack here. So what we are saying that there is a middleman in between here. To understand how much the weight affected the error, we need to understand how much the weight affected the prediction. So our prediction is our output, like this thing, right? So this is our prediction. And remember, we just did all of this. We just said that, like, well, our prediction is basically the whole thing right over here, right? Because we just realized it right over here. We just realized that, like, oh, okay, the prediction is actually like this thing is part of the prediction, this thing is part of the prediction, this thing is part of the prediction, right? And these guys are like, oh, hey, like, I might be part of the prediction, but I got my guys from these things, right? These things are also part of the prediction, and also the input is part of the prediction, but we won't change the input. We're just looking at, okay, which of these guys are part of the prediction? Well, these weights are part of the prediction, these are also part of the prediction, and these guys are saying, well, these weights are also part of me, so they're part of the prediction, and the input here is a part of these weights, so the input is also a part of the prediction. So what we're basically doing here, there we go. So this is basically the chain rule, is that we're saying, okay, weight 6, how big of a part are you from the error? And we're saying that to understand how much the weight 6 plays in the error, we need to, we can see that we split it up, and we need to actually understand how much of the weight 6 actually plays in the prediction. And then we need to understand how much of the prediction plays in the error. And that is, boys, ladies and gentlemen, something called chain rule. And chain rule is exactly what I am essentially trying to explain with all of this. I feel like I'm gonna say it for the very third time, because this is really important. This is like the fundamental of backpropagation. We're trying to figure out what is gonna happen if we change the weights. Will the error go up or will the error go down, right? And how we're gonna do it is looking at each single weight. And we start with weight 6. We start with this weight. So what we will do is we will look, okay, weight 6, how much did you contribute to the error? Or like, if we change weight 6, how big is the change in the error gonna be? Like, right, as I said before, if we increase it, is the error gonna go up? If we decrease the weight, is the error gonna go down? If we increase the weight by 0.5, how much is the error gonna go up? If we decrease the weight by 0.5, how much is the error gonna go down? The chain rule is saying that, like, well, we need to look at the middleman. We need to look at everything in between. And everything in between here, at least according to the statement right over here, that the thing in between here is the prediction. The prediction actually plays a role in the error, and the sixth weight is just part of this prediction, right? And once we figure out how much change in weight 6 does change in the error, we need to go through each of these weights. So then we need to understand, okay, how much does this play a role in the prediction or like in the error, right? And how much does this play a role in the error? And how much did this guy play a role in the error? And how much did this guy play a role in the error? And how much did this guy play a role in the error, right? And what chain rule is trying to tell us is that, well, if we are gonna, because right now we're just looking at one weight, so right now it's pretty simple formula, right? Like we're just the prediction is is the middleman, right? But if we're gonna be looking at this weight right over here, let's call it weight 4, right? Let's see, okay, how much did weight 4 change the prediction? Well, you can see that it's a byproduct or a part of weight 6. The most important thing. So you can kind of see that if we change, if we would start changing this number, this output would change, and then this output would change, right? Like you can see here, like as he is, don't mind all these numbers, we do not need to think about them. I recommend watching this. It's a very good supplementary thing. But I'm trying to simplify this even more, so it's even more understandable, or at least I hope so. And so you can see that as he's like decreasing the weight here, he is also decreasing this, and he's also decreasing this, and in the end, that will also decrease the error. Now that we understood what the chain rule is all about. Important thing, I just went on a math tangent, I just kind of realized. Now, the most important thing is that we can calculate this, right? And remember, this is not division. You don't need to calculate this bottom part. It's just stating the change, right? What is our error? Well, our error is this formula right over here, right? Where we have the predicted value, which is this, and our true value, which is this, which is going over here, right? And so we see that we can write a change in error. We can write it as 1.5 prediction minus actual value times 2. So this thing, like to calculating error, we can just set it in here. And to understand what our prediction is, right? As we calculated all of this right over here, we talked about it. We can take this and we can put it, what can we do? We can put it in here. So our prediction is because of all of this. And I'm gonna say it again, because I don't know why, it's just really important, because it really drill it into your heads, guys. Backpropagation is really confusing, but once you kind of like get the what we're trying to achieve, once you kind of like get the intuition behind what we're trying to achieve, it becomes rather simpler. So remember, this whole big formula is basically this whole forward pass that we just did. So the prediction, we're basically saying that the prediction right over here, so if we want to figure out how much weight 6 changed in the prediction, like if weight 6 changes, how much does the prediction change? Well, what is our prediction? Our prediction is all of this. So you can kind of see that the most important change that is happening is here. So if we would change this weight to 0.05, right? We would do 0.05. Well, how big is all of this? How much is the number gonna change here? So now that we have this understood, all of this, the chain rule understood, we understood that the prediction is part of this whole forward pass right over here. That's our prediction. And now we can do a very simple formula that to update the weights. So our update, I'm just going to do like a star here because to showcase that like we're updating it. So to update our weight 6, which is this thing, we need to take weight 6, take this, and minus the learning rate, which is usually like eta, something like this, and the change in error given the change 6, yeah, okay. And we can also, okay, so learning rate, a random new term appeared. A learning rate is how big of a step do you want the error function to change. You guys, I had a video on introduction to gradient descent or search space optimization, right? Where we were talking about this kind of stuff, right? And let's say our error, let's just make it like this. So here is a possibility of where our error could be, right? So let's say that currently we are 0.327, right? 0.327, let's say it's right over here, right? So we see that our local and global minimum is right over here. Maybe it's a little bit like I wrote, yeah, but let's just say our global minimum is right over here, right? What we want to know, right? First things first, what we want to know is which step to take to improve the error, right? So if we increase our weights, will the error go up or will the error go down, right? That's one of the things we want to know. Another thing we want to know is like, okay, well, how many steps should we go, right? So how many steps we should go is this eta. Yeah, this thing here means eta. And the eta is basically a learning rate. So our learning rate tells us by how big of a margin are we gonna like try to decrease our error, basically. So if we say that our learning rate is 0.01, right, then it's gonna go like in very like small steps. So this is like after one backpropagation, second backpropagation, next backpropagation. It will do all these. So you can see that another important thing is like backpropagation is a very like iterative thing. It's something that you do every time the neural network guesses it wrong, right? And every time a neural network guesses it wrong, you want to try to minimize the error that it's guessing. That's why we did all of this kind of, that's why we made the error into this, right? Because we want to minimize the error, right? We are here, this is our error is 0.327, right? And the learning rate is 0.1, so we will just move into that direction, 0.1, right? So we will have this big change in a negative direction, right? So the error becomes less, right? If we do it 0, if our learning rate is 0, or like if our learning rate is 0.5, right? Then our step, it's going to become even bigger, right? And we can also overshoot. Let's say our learning rate is way too big. Let's say our learning rate is like 5, right? Then we can actually overstep like this and increase our error. Meanwhile, while we're actually going in the right direction. But again, as I was talking about with this like backpropagation being an iterative thing, is that like you need to think about it like this is running it once. We want to run it multiple times, right? We want to train our neural network. We want to train it, right? So if we train it multiple times with learning rate of 5, what is going to happen? Well, it will never converge. It will go 5 over here, 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 5 over here. You can see it will try to go into the direction which gives us least error, but we will never it's just way too unstable, right? So what do we want to do? We want to use a lower learning rate. So now it's gonna go boom, 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 right? Each iteration of backpropagation will decrease our error. But there's also like a downside. If like our error is way too low, then you can see that like we're just going way too slow. Like our error is minimizing, but it's minimizing to the point where like it's almost minuscule. Let's say like you like think of just like which one could be faster, an error rate of 0.5 or 0.00002, right? Like one goes like between 5 iterations, right? One goes 1 2 3 4 5, boom, it's in the spot. Another one is like, yeah, well, this actually you don't need to draw all this. One is like 1 2 3 4 5, 1 2 3 4 5, yeah. Boom, we're here, right? We're in the global minimum, and the other one is still like crawling right over there. So you can see like this could kind of choosing the right learning rate is important to understand how well your algorithm can how well your algorithm is training, right? So this really quickly explaining what the learning rate is. So usually the learning rate is always usually the learning rate is a constant. So you don't want to change the learning rate during training, but you could change the learning rate during training. That's another thing. I feel like training neural networks, that's like opening another topic that's a little bit out of scope for our stuff, but it's really kind of like it's important to understand like, okay, wow, what is this learning rate doing? Like, wow, what is learning rate, right? Because it might be really confusing, or it might be like kind of like out of nowhere that we're just randomly making a learning rate in the formula, right? But yeah, usually during training, you want to have the learning rate. Usually you have the learning rate constant, but you can also change the learning rate during training. That is possible. So as I was saying with this error right over here, you can do that like after 10. Okay, now I'm gonna use some, because now we're coming to something called epochs. Yeah, I think we're gonna go there. Okay, so we're gonna be explaining epochs right now. So we have data set very quickly. This is gonna be very quickly explained. Data set. And an epoch, one epoch, is basically an iteration. The algorithm, our neural network, guys, remember this whole thing. Our neural network going through, getting fed all the data once. So that's one epoch. So you want to feed all the data into the data set. But as you guys might think, like, okay, but if we're like back propagating while we're feeding the neural network the predictions and everything like that, right? So wouldn't it be better to just do it multiple times, right? And that's why we have these epoch notations, because like we can do it in 2 epochs. And what is 2 epochs? Well, it means that we go to, the neural network goes through the entire data set 2 times. And you can train it for like, you can choose your amount of epochs. Usually even 100 epochs is quite an achievable, or like quite makes sense to train it for 100 epochs just to get this whole backpropagation right. Just to get this whole like, okay, we're gonna update the weights, just so that the neural network gets properly trained. And what we're talking about when we're properly training the neural network is backpropagation. Oh my god. Yeah, is backpropagation, is all of this. Backpropagation is the fundamental, all of this machine learning. I'm gonna be honest. Like deep learning, everything, neural networks, anything, backpropagation is the fundamental of all of this kind of thing. Until some crazy scientists find a way for us to use another method, this is usually this is the most widely, most common used backpropagation, the learning, right? And so again, back to the weight update. So we want to update this weight right over here. So as we were talking about with this whole like chain rule right over here, right? This is important because we have the error here, we have the actual prediction here, which is everything that we calculated. So now that we have understood that to predict change of this, you can see it's over here, right? So we're calculating change of this. So how do we get this? How do we get how much the change of weight affected the error, right? We need to finish solving this one. Here we do. Here you have 2 times 1.2 prediction minus our actual value or true value. Just right over here. To calculate change in error given the weight, we're gonna. I just realized I just went on a very big tangent. I'm so sorry. This thing is probably like an hour long. But I feel like it's really important to get this because backpropagation probably the hardest topic in my opinion in machine learning, because it's just very math heavy. But once you understand it, it's not even that complicated. But again, as we were saying, we want to look at this weight, right? And what is this weight saying? Well, it's saying that like, well, the reason for my error, my contribution to my error, wasn't only by me, because there were people behind me, right? H2 is also responsible, right? And H2 is like, well, I'm not the only one that's only responsible. It's also these 2 guys, this weight and this weight is also responsible. And the weights here are saying, well, the input is here is also responsible, right? So this responsibility, we're trying to put it in here. So we're trying to, like, all of this right over here, we will only look at weight 6. So here you can see we kind of have like this top place as well. We kind of included the top side of this. So we can actually, because the focus is this, right? We actually don't need these things. We only need this. And yeah, we don't need itself as well. We don't need this. How big of a part weight 6 plays in the prediction? the things that also affect it are these things right over here, right? We need to see that like the input and the weight 3 and the input 2 and weight 4. And that is, well, this is our H2. Because H2 as, yeah, what we just calculated. Okay. So you can see, so H2, all of this forms H2, right? So H2, you're a byproduct of these two calculations right over here. The weight is saying, well, my responsibility, or like the responsibility for the error, comes also from this guy, and these guys are saying, well, the responsibility for the error, my responsibility for the error comes from these things as well. And so this is where the word backpropagation comes from. We're trying to backpropagate it through these nodes. And we are focusing on H2 because that's what this weight 6 is part of. It's connected to. Okay, yeah, connectionism. Another fancy word. But connectionism basically means that like you can see that how everything here is connected, right? Like how weight 6 came from or was connected to H2, and H2 is like connected to all of this, is connected to weight 4 and weight 3, right? It's connected to weight 3 and weight 4, right? Here we have weight 4, weight 3. Okay. And now you might be wondering, well, why did we do this? Why are we taking this and giving it here? Like, what is going on? This is derivation. Derivation, because we're doing this thing, which is also called derivatives. Derivatives. It's a very high school calculus thing. The most important thing to know about derivatives is that, like, let's say you have x4. How do you derivate x4? Well, you put this one here and you do 4 minus 1 basically. So what's gonna happen here is that we'll do 4x3. So this is the derivative of x4. Boom, easy, right? Well, you might be wondering, well, what about the derivative of x2, for example, right? Well, you put this one here, minus 1, it's just going to be 1, right? And so the derivative of x2 is going to be 2x, just 2x, right? Without any exponential. And now another most important thing is the derivative of x is always going to be 1. Mathematically, this x can also be written as x exponent 1, right? So technically what you're kind of doing, you're doing x minus 1 minus 1, and then it becomes 1x0, and then it just becomes 1. So yeah, so okay, the derivative of just x just becomes 1 given this proof. I don't even know if you can call this proof, but yeah, given this kind of logic, right? So just remember, like, a quick way to calculate derivatives can be do this. There's yeah, I mean, derivatives is a very mathematical thing, you guys. The only important thing for machine learning is knowing how to derivate these things that I just talked about, like, right, the derivative of just x is 1. And x can be whatever the hell, right? So if it's 7, the derivative of 7 is still gonna be 1, right? Because it's x can be whatever the hell. Make it like 2, 5, 5, 5, 5, 5, 5, 5, right? Still, the derivative of that is still gonna be 1, because x is just a given number, right? It's just so, if you guys are wondering about that. And so what we're doing here, we're taking the derivative of this, right? We're taking the derivative of this, and we are, again, as you guys are doing, minus 1, putting 2 here, right? And this is the reason, like, this is the reason why we're doing this right over here, 1.5 in the formula, is just to make it simpler, right? Just so we do not have to calculate this, because these cancel out. They become 2, which 1 and 1 times prediction actual is just going to be the same value without any change. So you can see we're literally doing this. We're literally applying this 1.5 just to simplify the formula. Oh my god. I'm sorry guys, it's just something about me feels like I'm taking too much time to explain this. So I'm sorry about that. Now back to what we were talking about. Now we know why this is happening. We're taking the derivative, right? We're calculating it, and then we're taking the h2, which is all these weights summarized, right? Like this weight and this weight, the sum of these weights. And sum, what is the symbol for sum? This sigma right over here, that's sum, right? So when we're summing something, we use the sigma symbol. That's why when you see a perceptron, they're gonna have this symbol. And that's what it means. I'm trying to fill in all the gaps for all the people who are like very like, what the hell is going on in backpropagation? I have no idea. I'm trying to fill in as many gaps as possible. And so okay, so and now we have summed all of this. Use this. Oh my god, my sigma is really bad, but yeah. So we have summed all of this, which is going to be h2, and we can now say that the change in error given weight 6 is going to be our predicted value, which is called prediction minus actual, and then times h2. Boom. That's because we just simplified it, right? h2, all of this, right? We just asked, well, how much did I affect the error? Well, I affected the error with this guy, this weight and this weight and the inputs, and so you understand it. Okay. So back to this formula, right? We need to update our weight, right? Oh my god, yeah, I forgot. Here we can also say that the error is changing E6 is actually happening because of, okay, just to simplify, we can say that this delta means prediction minus actual value. So this thing. So delta is this thing, so we're just putting this into a delta. We're just writing delta h2 just to make it simpler, right? And so this whole error, or like this whole thing that we have right now, we can say that just made as delta in h2. This delta basically means prediction minus actual. Now we have a formula to update our this weight, right? And to update, let's do it like this. This is weight 5, weight 4. This might be a little bit confusing, but remember, weight 3 is this, and weight 4 is this, and weight 1 and weight 2 is these ones. The reason we want it like this and not the not counting from here is that we just want to kind of like have like a clean view that like, oh, okay, this is like h2 is part of 3 and 4, h1 is part of 1 and 2. So it's like, it's very simple, you can very clearly kind of see it, right? And yeah, so we just basically whatever we just did here, actually, yeah, we can just take all of this and make it a little bit more. Just do delta. So this is the weight. So now we know how to update this weight. Now we need to know how to update this weight. Well, it's the same thing, except for this time it's H1, right? So H1 is the reason for weight 5 to do its shenanigans, right? And then we need to update these weights, right? And we need to, let's, again, we start from right to left and we go down first. So we can do this, we can write it this one. So we need to update weight 4. And to update weight 4, the change in weight 4 will be weight 4 minus the learning rate. So we're basically asking like weight 6, okay, how much can you update, can you change this error with, right? And the weight 6 is saying that like, oh, well, yeah, if you change me, you will also change something in H2, right? Because H2 came from me, basically. And the same with the fifth weight, right? Like the fifth weight is saying, okay, well, if you change me, you will also change something in H1 because I am not the only guy responsible for the error, right? And so in weight 4 here, you can see we're kind of getting a little bit more deeper. Before we were between the hidden layer and the output layer. Now we're between the input layer and the hidden layer. We're asking weight 4, well, how much did you contribute to the error, and were there anything that was like chained to you? Like, were there anything that was like affected by you, right? And then weight 4 is saying, well, the input is all the reason I got calculated with the input to predict the error, to make the prediction, and the prediction, I got calculated with the input to make the prediction, and then the prediction did the error, right? And weight 4 is also saying that like, well, also weight 6, I got calculated before weight 6, but weight 6 was also seen by my calculation, and then he was also part of the prediction, which again was part of the error, which is like kind of visually how the chain rule works here, right? So we basically want to mathematically see, okay, like what are you like chained to? What are you like connected to? Like, right? So it's saying that like, well, the input, I was calculated with the input, and then I was passed into the calculations with the weight 6, and then the weight 6 made the prediction, and then he was part of the error. So technically, like, my contribution to the error is through weight 6 and through the prediction, and then that's how I did my contribution to the error. This is very easily notated like this. Here's our input times the prediction, and also we need to add weight 6 because weight 6 got passed along with it in the prediction. And this is the formula for updating weight 4. And weight 3, now that we kind of know, now this is basically the formula between the input layer and the hidden layer, right? You can see here that, okay, so weight 3, it's this guy, right? And then we ask this guy, well, how did you contribute to the error, or what happens when we change you? Well, I got calculated with I1, I got passed into the weight 6, and I was part of the prediction, and the prediction had like this true value, and the prediction was wrong because of this. It was wrong here, and how much it was wrong by, it's the error. And so in the end, yeah, I contributed to the error through chaining, basically chain rule, through all of these, through being passed through my calculations, being passed from this input into my weight, into then this weight, into then the prediction, right? And so exactly the same as, or like the same notation as we did because this time it's I1. It's the first input that the weight was part of. And the delta here, I'm gonna be honest, I don't, like, I look at the notes, and in the notes they wrote a delta, but I think it's a little bit misleading to write it like this. It's because they say that in the notes the delta is the prediction, right? So the delta is remember, prediction minus true value, or that's true value. So in our case it was 0.91 1 minus 1, right? Prediction true value. Remember, this is the delta. It might be a bit misleading, I'm not even gonna lie. Usually I'm kind of come from the fact that deltas are derivatives, but it's completely fine. I guess they choose their own notation. Oops, this is wrong. I should see. Okay, so what was the weight that was part of me? Weight 6, right? Weight 3. What was the weight that I was passed into? I was passed into weight 6. So weight 6 is in the end what contributed to it. And then we do change in weight 3. Weight 2, actually. We do weight 2 minus eta. And okay, so we're looking at weight 2, right? And weight 2, well, I got my input was I2, so I2, and then I got passed into weight 5. And then I was part of the prediction, which in the end made the error, right? Part of the prediction, which is delta. And I'm running out of space. Cannot believe it. Okay, part of the prediction. It's actually, there we go. I was part of the prediction, and in the end, weight 5 was the one that affected me. I hate when I do this. Okay. Yep. So weight 5 was the one. Oops. Weight 2. Yeah. Weight 3. Weight 2. I was part of weight 5, and then I was passed into the prediction, which then made the error. Might have made a mistake. I might have highlighted this one that is wrong. My bad. I'm sorry for that. This is the weight that we're talking about. We're talking about weight 2. So the weight passes through weight 5, which yeah, okay, I've already explained this. Okay, so here's weight 5 that it get passed into, and then we do it now for the last weight, which is going to be the last weight. So basically what this formula means is like to update weight 2, right? Like the new values for weight 2, which is 0.21, right? They're gonna be the current value for weight 2, 0.21, right? Minus the learning rate, which we talked about what the learning rate is, but we do not, the thing about it is like usually the learning rate is given to you. For example, like if you're on an exam, people are saying like, oh, the learning rate is 0.5, like, right? Calculate or update the weights, right? Now you know that like, oh, okay, the learning rate is 0.5, we just put it in here and we do the calculations, right? And remember, yeah, the delta here is the prediction, which is prediction minus true value. So here's our prediction minus true value, also used to calculate the error. Brief summary, and minus learning rate, then I, and then how much does the weight. Now we're looking at weight 1, well, you're coming from I1 as well. You're coming from the first input, and then you get affected by the fifth weight, and then you make the prediction, which then leads into the error chain rule, right? You make the prediction, and you're also affected by weight 5. Holy moly! Oh my god! And now we will see the beauty of matrix multiplication coming in again, right? Because now we have written all of these instructions, right? We've written all of this, but what if how we can quickly and mathematically update what if I told you that instead of calculating all of this, we can also really quickly calculate it using matrix multiplication, right? So instead of calculating all of this, right? Instead of like, instead of like writing it, putting in the values that like, oh, okay, weight 1 is, let's see, weight 1 is 0.11, right? So we have 0.11. Our learning rate is minus 0.5, right? Our input value is let's see, our input value is 2, right? And then we need to multiply it by that predicted value minus the true value, right? And the predicted value minus the true value, oh my god, 0.819. Is that correct? Right? Oh my god. Yeah, I'm sorry guys, I feel like I've been explaining this for too long, but yeah, you have this is what you get from doing this. Oh yeah, it's also a minus, right? So it's negative, but yeah, also we do like the negative 0.8891, right? And then we do the weight for the fifth one, right? 0. like times 0.14, right? And then we need to do all of this, and then we equal that, right? And then let's say we get like I'm sorry guys, too little sleep. Wait, it's actually 0. Yeah, I'm so sorry guys. These small little mistakes here are just okay. There it is. Okay, and then we do the multiplication, and then we get the answer that like, oh, okay, the weight 1 is gonna be then 0.12 or something, right? Let's just say that, right? Yeah, you can see how kind of like, okay, this just takes too much time, right? Doing it individually, right? Doing it individually, one by one, takes too much time. So here where matrix multiplication also comes in, right? So we can write this whole thing, we can write all of these things as a matrix multiplication. We can say that weight 5 and weight 6. So we can update our weights in a matrix, right? We can just update it in the matrix. And then we do weight 5 and weight 6. So we take the values, the old values, 5 and 6, these two, and then we do minus the learning rate and the predicted value times the predicted value, and these things as I was talking about, h1, h2, right? h1, h2, which is both of these, right? What we can do is we can put these, we can multiply these into the matrix, right? So now our function becomes, not a function, now our formula becomes simpler, where we can do the learning rate h1 times h1 with the delta, and then you do the learning rate times h2 with the delta, right? And now and that's this thing right over here is how we figure out how we update the weights for 5 and 6. Boom, we just did it. Like this whole notation, like imagine like I just did one whatever the hell. Yeah, I just did one formula manually here with matrix multiplication. Boom, very easy, right? Like we just did two at the same time. You can do two at the same time, so you can see how matrix multiplication can be computationally much less expensive, right? When we were talking about like you're coding this in Python, right? You're using NumPy libraries. It's so much more easier, so much less computational power that is needed, that is required, right? So now we just did weight 5 and 6. So we just did the weights between the hidden layer and the output layer, right? Now we just need to do it between the input layer and the hidden layer. So all the weights between the input to hidden, like between the hidden layer and the output layer, we had weight 5, weight 6, right? Now between the input layer and the hidden layer, we have 4 weights, right? So we just have to, well, what are we gonna do? Well, we put all of them into the matrix multiplication. Actually, to make it even more simpler, I can make sure so you guys understand where the weights are coming from. And then now you do weight 1. So to update these weights, you need to have their current weights, right? So you take their current weights, and which is like I think it's like this then. I think using equals. Okay, no, yeah, but then you have this, the learning rate delta, and now because we are between the input layer and hidden layer, we need to take into account the inputs, right? So as we were talking about here, right, it's the same thing here. Now we take into account the inputs, and we can put the inputs into a matrix. Woohoo, right? To simplify our computation. And then we also, again, weight 5, weight 6, right? Is also a part of, okay, so the weights that are between the input and the hidden layer, they are passed, or like the calculation is passed further into between the hidden and the output layer. And let's say we do this weight 2, right? Like it's passed, okay, here's your input, it's going in, it's going through the hidden layer, now it's going through the 5th weight, and then it's in the output layer, and then it makes the prediction, and then it calculates the error, right? And so we can write that we see that like it's affected, v2 is affected by w5, right here. So v2 affected by w5. So when it goes, it gets affected by this thing, and you can see here, here's the notation. I mean, we went through this, so I'm trying to kind of like just very quickly skim through this, but also at the same time tell you what is going on so it doesn't feel way too out of hand. Here we have weight 5 and weight 6. Okay, so now that we did all of this, can we simplify, or can we make this even more simplified, right? Actually, we can. So this thing here can be written as W1, W2. And then what we can do now is that we can, as we did it here, where we combined these ones into each of their into the matrix, multiply them into the matrix, we can do the same here. We can multiply them, or like, yeah, we can combine them into the matrix. So we have this, and then you have the input, the predicted value, or the predicted value minus the true value, and the weight 5. And then we have another one, which is the learning rate, I1. You can see learning rate, predict value I1. We put them into here, right? And then we have, oops, I1. So you can see that this matrix goes down, meanwhile this one is in width. So you can now we have multiplied I1 with this. Now we just need the I2 with this and this. And then we have eta I2 delta W5 make it a little bit eta I2 add the predicted value minus the true value. That's what our delta is actually representing, just so it's not being confused with something else. And boom, and that's our matrix multiplication right here, simplified, right? And now we just need to put in all the numbers, right? Now we just need to pull in all the numbers, but don't worry, all the numbers are here, right? Like all the numbers are here. We have the formula, we have like all of this. These matrix multiplications, they're basically calculated from these formulas right over here. So we just put them into matrices so we can calculate them in mass, like everything at a time, right? So we can calculate everything instantly. And so yeah, so now we can do the calculation for this first, right? So to first do the calculation for W5 for the 5th and 6th weight, right? We do we see, okay, what is its current weight? 0.14, 0.5, right? Then we go here, we put it into the matrix, because remember, we have, here's our, we do our current waves. You can see 0.14, 0.15, right? Because from our current weight 5, weight 6, and here in our neural network 14, 15, right? And what we also is going to need the learning rate. We just randomly said that the learning rate is did we set our learning rate? Yeah, we did not set our learning rate. Usually if it's like an exam or something, they will probably tell you like the learning rate is 0.05, for example, right? So minus the learning rate, so you can see in our formula, minus the learning rate, minus the predicted value minus true value, and predicted value minus true value, if you guys remember, we calculated right over here, actually. The predicted value right over minus the true value, which I said was like, yeah, I had like a miscalculation sadly, but this is the correct one. And minus yeah, true, so we do 0.809, so that's our delta. We're just gonna put that in. So we're gonna make it so that it's times minus 0.8809, right? And then what's next? We look at our formula. What's next is H1, H2. And H1, H2 is already calculated, right? Okay, now this is something really important, that like we do not have any activation functions here. Activation functions basically means that like let's say we have like a ReLU activation function. A ReLU activation function, if this is like an axis, right, it kind of goes, it really goes like this, right? Boom, like this. So if the output of the perceptron is negative, then it's gonna output 0. Else it's just gonna output whatever the number is, which is like S is just gonna output 8.5. So you can say that like you can argument that like either we're not using our activation function here, or like that we're using ReLU as our activation function. There are different activation functions that give kind of like different results. For example, sigmoid, for example, sigmoid function, and a sigmoid function can only go like between 1 and -1, for example, or like there's also activation functions that go like between 1 and 0, for example. And so then this calculation, because like it depends on what activation function we're using, right? Just remember that if you're using sigmoid, for example, you also need to derive the activation function. You also need to make a derivative of the activation function when we did this whole chain rule. Yeah, when we did this whole chain rule stuff here. So so here when we're doing when we're calculating the error and we're focusing only on the W6, right, and we said that it's from H2, we also should we need to kind of like use the derivative of the activation function, because let's say that like the actual output is 84, right, but our activation function makes it 1. Well, whether we give 84 and 1 to say that like, oh, that's like what affected the error, is going to be a very big difference, right? So that's why we need to kind of like that's why we need to kind of like figure out, okay, what was the value before before it got made into an activation, into a sigmoid activation function, for example, right? And that can be extra. You guys can if you want to, you can just Google that or anything like that, how to like make backpropagation with like a specific activation function. I feel like I'm rambling at this point. I feel like I feel like I've kind of like already dragged this video a little bit too much, but I'm gonna be honest. I hope you guys learned a lot. But yeah, now we do following the formula H1 H2. Right, so we have 0.85, 0.48, and where does 8548 come from? Well, it was from the forward pass that we just did, right? And that's it for a formula, right? Yep. Now we can just simplify it, or like we can put these values into the matrix. And how do we do that? Well, still the same. 0.14, 0.15. We just want to do these values, multiply them. Oops, multiply them in here. So both of these go in here, and then both of these go in here. And so do 0.14. Remember, it's this 0.15, which is the weight from this. You see here, and then we do minus, and then we're just gonna do the calculation. We're just gonna output the number. We don't need to calculate this, but you guys understood this. We're just multiplying all of these together. So multiply all of them together, we're gonna get like 0.034, 0.019, right? And then in the end, as you can see, we will do matrix addition. So we just do this matrix minus this matrix, which is really simple. And in the notes, we're just rounding them to 2 digits, 2 decimals, I mean. So let's do 2 decimals, 0.17, 0.17. The same. Yep. There we go. And so this is our new weights. This is going to be our new weights for weight 5 and weight 6. boom, now our neural network has learned the new weights because it adjusted. What it just did right now is just it adjusted based on the error using these derived formulas that we had. All of this, we found new weights, and so we are kind of like, again, learning rate. We just did, when I explained learning rate on all this kind of stuff, we just did one small step in this direction. So it might not, we kind of minimize the error. We try to minimize the error for this specific input, right? Just remember that as well. It's like for this specific input we minimized it, right? But it might, if we get a whole different input, right, and with new weights, well, then it's gonna be different, right? So it's like a constant kind of like training and fitting into the training data. Like you want this model, you want this a neural network to kind of fit into whatever the hell you're giving it. Here we calculated the weights for the first two, right? Now we need to calculate the weights for these. And holy moly. Okay, so we are so close, guys. Don't worry. We are very close to finishing this off. Okay, so we have the weight 1, weight 2. Let's, for color correction, weight 3, weight 4. Let's keep it a little bit consistent. I know I wasn't consistent here, but just to kind of at least have some consistency. We have 0.11, y 0.11. We look at, well, first we can look at the formula, and we can see that, yep, you can see here, we take the current weights we have. So to make the new weights, we take the current weights we have, and then we minus all of this. So our current weights are going to be here. So our current weights are 0.11, 0.21, right? Yeah, 0.21, which is weight 1, weight 2. 0.21, and yeah, I'm not gonna say all of this again. I'm just gonna put them in 0.12, 0.08 because of this 0.12, 0.08. We are between. You can also, guys, think as well, like, okay, which layer are we propagating between? We're between the input layer and the hidden layer. Of course you can have multiple hidden layers and stuff like that, but once you understand kind of like how this works, or like once you understand that, like once you understand the fundamental here, like all of these derivatives, what we're trying to do, what we're trying to find, we're trying to update weights, we're trying to figure out how much these things are like chained together because of the quote-unquote chain rule, and we want to also see how much each individual weight affected the error. Like once you kind of like get that like as like a basic understanding of backpropagation, it's really becomes just kind of like applying the formula and just setting in the numbers. And so it like the most important thing is kind of like understand that like what we're trying to do here, right? And understand also that like matrix multiplication is king. That like it's so important that like computers nowadays have they're making chips. There are they call them AI chips, but in reality they're solely made for matrix multiplication, and that's what those AI chips really are. And so the learning rate, which we know is like this 0. Yeah, you guys can see we basically the same formula here and the same formula as it is here. So you can see like it's pretty much the same because it's all coming from this. It's all coming from, yeah, this thing. And so we're just putting it into a matrix. So you have 0, 9, and then now the only difference is that we also add the input layers here, right? I'm gonna show yeah, all of these inputs. So we're adding all of these inputs, and then we do 0.15, which is 0.14, 0.15 is these ones, weight 6 and weight 5, right? Weight 6 and weight 5, 14, 15, yep, understandable. And now we just calculate it, so I'm just gonna make it on a new line. So I'm just gonna be a little bit lazy here, just copy this, and then we're gonna do minus, and then we're just gonna yeah, I mean, then we're gonna be skipping some steps, but then you guys, if you guys remember what we did here, basically the same stuff. We want to just put this, multiply these two together, then put it in here, and then put it in here, or like multiply it with this, and then multiply it with this, and then the value that you get, multiply these together, then you multiply this with this, and then you multiply this with this. The output of this is going to be minus 0.011, 0.017. Okay, another topic that is important is that, like, you can notice how these things are very small. Like the multiplication, like as you can see, like the weights that we're gonna be, like the numbers that we're updating them by, they're kind of very small, and that is actually a problem, a common problem that is called vanishing gradients. So vanishing gradients is really kind of simple concept. It basically means that, like, because our values are so small, they can actually be so small that the change that we're updating our weights with, let's say weight 1 was 0.01 or something, right? Or a 0.2, right? Or something like that, right? And the new weight, after applying our gradient, which, yeah, essentially it's a gradient, after applying our new weight, is still going to be 0.2. So even after updating the weight will still be the same, which is the vanishing gradient problem, right? So this is kind of like the problem is that, like, our values can actually get too small, right? Too small to the point where we barely see any, where we don't see any difference, right? Like they vanished, they're gone, right? And yeah, to kind of to combat this, of course, we could like round it, right? So we can like say that, like, oh well, okay, this is gonna be 0.01 or something, right? Like just something, right? Because you cannot, you kind of have to like round it to something, just to kind of have like a little bit of an increase, right? So this is kind of like the vanishing gradient problem. Really simple, really like nothing really much else to say apart from like, yeah, this is a thing, and just be cautious of it. And so yep. So now we have calculated these two together multiplied by this, then multiplied by this, then they are multiplied, then this one is multiplied by this, and then this one is multiplied by this, and we get this outcome. And and now, in the end, again, as we did before with this matrix addition or subtraction, and we will do this matrix subtracted by this matrix, and because these values are already negative, negative, and negative, gonna be positive. Very like fundamental math concept. And then we do, it will in the end be 0.12 and 0.23 for the first two weights. You can even, we can look at our cheat sheet right over here. Yep. Okay. So yeah, you can see it's going to be weight 1, weight 2, weight 3, weight 4, right? So for weight 1 here, weight 2 here, our weight 3 is 0.13, and our weight 2 is 0.10. And I notice I didn't add any zeros, so let's add a 0 here just so it's more readable, because I am consistency is important in visual design. And so these are our new weights that we update. So in the end we can actually do it at 0.12, 0.23. So this one in the end will be updated to 12. This one will be updated to 23. 0.13, but then this one be updated to 13. This one will be updated to 10, right? Yep. And then we have 17 for both, so it's kind of easy. You don't need to think about which value or which weight is which. This one is going to be 0.17 and 0.17. There we go. And now we have updated our values, and we successfully performed a backpropagation on our algorithm. Oh, thank you very much for watching, guys. And after saying is also like, okay, what do we do now? Do we put in the same values? Usually you move on with the data set, so you put in something else with the data set after the prediction is wrong. But yeah, I think that if you put in the same values, that will kind of lead to overfitting. But that's if you don't know overfitting and stuff like that, don't worry. If you know backpropagation, you will certainly know a lot more about machine learning. And you'll figure it out, don't worry. And this was a lecture in backpropagation. Thank you very much for coming. I hope it is at least a little bit more clear now that we've done everything and we've explained the chain rule and how we want how this is not division. We're trying to find how much did change in W affect the change in the error. We understood why matrix multiplication is so important, as it can help us just compute way faster than doing it single-handedly line by line. We understood that like once you output the prediction of a neural network, you need to compare that prediction with the true value, and if the true value is incorrect, then we will do backpropagation. If it's correct, then we did it, woohoo, yay. Like our neural network was correct, we go to the next data set, the next input, next set of inputs, right? And we also calculated the forward pass, which meaning that how it goes from the input into the prediction. This is the forward pass. And yeah, that's everything there is to it. I think I've said everything for the most part. We can maybe even zoom out. Yeah, we can't zoom out. Yeah, we can even zoom out and see how much we have done. Yeah, look at all of this. This is all us. Good job, everyone. Thank you. Thank you for watching, and I hope now you know backpropagation by heart. And goodbye.